Welcome to a new series of Coonrod's Corner videos, the real world of RF printed circuit boards. Today's topic, material properties and fabrication effects to consider when designing for microwave and millimeter wave antenna applications. Now here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation, and I am a technical marketing manager. Today I'm going to be talking to you about antennas, specifically microwave and millimeter wave antennas, and I'm going to be looking at some of the material properties and also some of the circuit fabrication effects. Now this is a really big topic. Antennas are pretty complex, and just for a short video I'm just going to give you a few highlights of critical things to think about. But if you do want more information, I invite you to go to our Rogers Technology Support Hub, and there you can find much more information on this topic and related subjects. As well, you can also on the Tech Support Hub contact an engineer in your area. So with that, let's go ahead and get started. First off, I'm going to talk about the antennas in a very simple way. I'm going to just talk about microstrip patch antennas, or maybe patch array antennas, and also the transmit function only. So that just makes it a little bit easier to go through some of the concepts. So first I'm going to talk about the antenna concepts themselves for a microstrip patch antenna. After that I'll talk about some of the material properties that are critical and why, and then also some of the circuit fabrication influences that can impact antenna performance. Shown here is an illustration of microstrip patch antenna showing the signal on top and ground plane below, which is not shown. So we're looking at the signal image only, and upper left is showing a very simple patch radiating element with a feed line. Feed line is usually 50 ohms. The patch is usually a very low impedance, maybe 1 ohm or even less. And that impedance difference between the feed line and the patch will cause reflections, so a lot of energy coming down the feed line is going to get reflected right back at that big impedance transition at the patch, and the patch is not going to receive as much energy as it should. So because of that, we a lot of times put in impedance transformers between the feed line and the patch, and essentially trying to make that transition between the higher impedance and lower impedance a smoother transition and having less reflections, and that way you get more energy to the patch to radiate and transmit. So the formulas for the basic microstrip patch are shown here, and the length of the patch is really the standing wavelength of the radiating energy anyway. And you can see on the bottom right, I've shown some of the fringing fields that are responsible for the radiation in transmit mode. And it's good to keep that in mind because that also helps you understand why some of the circuit fabrication influences can have an impact on antenna performance. Shown here is more information about radiation, and this is really important to understand for antennas. Again, we're really thinking more in the transmit mode where you're wanting to radiate energy. Now, insertion loss is made up of 4 different components, and they are all summed together. And what we have for insertion loss is dielectric loss, conductor loss, radiation loss, and leakage loss. And typically, you do not want radiation loss unless you're wanting to transmit and radiate energy. Then you do want radiation loss, but only at the patch. So the feed line that's bringing energy into the antenna structure, that feed line should not radiate, and if it does, you lose some energy that way. You really want the feed line to have no radiation loss and the patch to have maximum radiation. And with that kind of thought, then let's take a look at some of the relationships here. So the frequency relationship basically is as you go to higher frequency, there will be more radiation or radiation loss. Also, the circuit substrate thickness. The thicker the substrate, the more radiation you will get. Also, dielectric constant matters, and a higher dielectric constant will have lower radiation, and the opposite's true. Lower dielectric constant, higher radiation. And that's also why you see in a lot of antenna applications a lower dielectric constant. Now then, the different structures also matter. So a microstrip circuit will radiate rather easily. Grounded coplanar waveguide to the right there, that will also radiate, but you can design it where it does not. And sometimes it's a combination between grounded coplanar waveguide for the feed line, so the feed line does not radiate, and then it transitions to microstrip for the patch to radiate. And then also you can do the same trick with strip line where it will not radiate, and then you can bring the feed line through the strip line and then via up to another layer that's not shown that could be a microstrip patch, and then you can radiate from the microstrip patch. For antenna applications, there are several material properties that are critical, and there's also several things to think about for circuit fabrication that can influence the antenna as well. So the next few graphics I'm going to show, I'm going to talk about the material properties that are critical and why, and then also we'll talk a little bit about circuit fabrication and how that can impact the performance of antennas at microwave and especially at millimeter wave frequencies. The information shown here is related to material properties, and there are several different properties to think about. First off, most of these properties are geared toward causing radiation for the antenna patch itself. And a thicker substrate will do that, so that's one thing to consider. Having a lower dielectric constant will also increase radiation. That's another good thing to consider. Having low profile copper or smooth copper, that will cause less losses of the conductor itself and more radiated energy. And then the low TC-decay is how much the decay will change with temperature, and having low TC-decay is a very good thing to have more stable performance over cycling of temperatures. And then low moisture absorption is always good, because when you absorb moisture into a circuit, basically that changes the properties, changes the dielectric constant and the losses. And then finally, high thermal conductivity, that's more related to high power and being able to get the heat out of the circuit. And many times that is important, because you might have a feed line with a lot of power that then gets distributed to many different patch elements. And the feed line itself will probably be carrying a lot of power, which can heat up the circuit. Shown here is a list of materials that have been used in many antenna applications, and for a variety of reasons. You can see differences in decay here, low losses, dissipation factor, DF, TC-decay, and also thermal conductivity. Just to give you some quick guidelines, TC-decay, normally if you have a TC-decay of 50 parts per million per degree C or less, that's considered good. And also for thermal conductivity, 0.5 or greater is considered very good. And you can see some of these numbers are very good for thermal conductivity and TC-decay, as well as dissipation factor. And again, lower dissipation factor is good, because having less losses will cause less heat to be generated. The material properties for antennas are very important, obviously, but also circuit fabrication. There are several things in circuit fabrication that can be very critical to understand, and it's always good to talk to your circuit fabricator about some of these issues. And you can also talk to Rogers. We have a very good technical support team that is heavily involved with circuit fabrication. Now, some of the things to be mindful of are probably obvious for circuit fabrication, like the conductor width and how well that's controlled, as well as copper plating thickness and a variety of other things. But the next few graphics, I want to explain a little more detail of some of the tricks that you need to be mindful of when you really get to higher frequency. An antenna designed at millimeter wave frequency is typically more difficult than microwave frequencies for a variety of reasons, and I'll touch on that in the next few graphics. What I have shown here is a simple microstrip patch antenna. More specifically, it's a microstrip series-fed patch antenna, and this is a structure that's pretty commonly used at 77 gigahertz for a lot of the automotive radar sensors. And you can see that as we designed this, there is 90-degree corners inside and outside. And then if you actually look at the circuit that we built to the bottom right, you can see those 90-degree corners are not 90-degree corners. They have some rounding or a radius. And that's very common with etching the circuitry. So at lower frequencies, the difference between the sharp corner and the radius really doesn't matter much. But when you get to higher frequencies and you have these very small wavelengths that are more sensitive to smaller anomalies, then the surrounding of these sharp corners can make a difference in the actual circuit as compared to the model that might be done with these sharp corners. So that's one thing to keep in mind. The graphic shown here is testing that we've done with our antenna test vehicle that I showed on the last graphic. And what we're doing here is testing the antenna at different temperatures, 25C, 65C, and 125C. And we tested the same antenna design on several different materials that had the same dielectric constant and roughly the same losses. And what we find is the Rogers RO3003G2 material has very little difference in frequency due to operating temperatures changing. You can see as a frequency shift about 24 megahertz, which is equivalent to about a decay shift of 0.002. That's very minimal. And then the CLT-MW, same thing, very minimal change due to a temperature change. Now the competitor material that's PPE-based, some PPE-based materials are better than others by formulation. And this is kind of a common material I've seen for both of these for properties of PPE-based materials. And you can see that the frequency shift is much greater than the Rogers materials, as well as the equivalent decay shift due to these temperature changes. In summary, I've talked about antennas for microwave frequencies and millimeter wave frequencies, and the antenna is pretty simple. It's a microstrip series fed patch antenna. And you can see that there's several material properties that I've shown that are very critical to make sure these antennas have the best operation and the best performance. And also there's circuit fabrication issues to consider. I just showed a couple quickly, and one of them is related to circuit etching, but there are many others, and we always invite you to talk to your circuit fabricator about these issues, or you can talk to our Rogers technical support team, which gets heavily involved with circuit fabrication, and that would be very helpful. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.